Okay, so when we last left off, we discussed and we focused on predicting the products from acid-base reactions. So I'd like you all to take a moment and look at the following. So hydrogen sulfide is a common gas that's generated. You can just as easily write it with an aqueous symbol. It's subjective whether the hydrogen sulfide remains dissolved in solution or whether it escapes as a gas. Both are acceptable answers. It will usually, in these kinds of reactions, escape the reaction mixture as a gas, but it would be appropriate, and it's also appropriate for you to write it with the aqueous symbol, because it's hard to tell, depending on the reaction and the temperature, whether the gas remains dissolved or whether it escapes the solution. Does that make sense? Hydrogen sulfide is a common gaseous product generated from these acid-base reactions as a result of the hydrogen sulfide escaping the solution. Does that make sense? Perfect. Okay, so let's take a moment and let's look at the following reaction. Let's try to predict the products of the reaction. Write a balanced chemical equation, total ionic equation, and a net ionic equation for this reaction. So let's take about 3 to 4 minutes and try to first identify our acid and our base, and then go about writing out your conjugate acid and conjugate base and predicting the physical states of each of your products. So don't be shy to message me with your proposed response for the products from this chemical reaction. Just as a hint, there will be a total of 3 products from this chemical reaction. And once you have your equation, you can message me your balanced chemical equation, and then finally your net ionic equation. So let's take about 4 minutes to work on this, and then we'll discuss. And really focus for this type of reaction of identifying your acid and your base. And we'll discuss in about 2 to 3 minutes. Don't be shy to message me in their chat, so that way I can provide you some feedback on your proposed reaction products and your proposed equation and net ionic equation. Any questions on this problem? Okay, so let's discuss this problem. So ammonium chloride, is that an acid or a base? Ammonium chloride, is that an acid or a base? Is ammonium chloride, it's a weak acid, yep, okay. And silver hydroxide, being a hydroxide salt, will function as our base in this case. Okay, so first things first, ammonium chloride is a soluble ionic compound. Is silver hydroxide soluble or insoluble? Is silver hydroxide soluble or insoluble? It's a hydroxide salt, and hydroxide salts generally, are they soluble or insoluble? I see people typing solid, that's correct. It's insolubles. Hydroxide salts in general are insoluble except for a few exceptions. So now what we're going to do is we're going to take each of our compounds and we're going to dissociate our soluble ionic compounds. So we get ammonium and chloride ions. Okay, we leave silver hydroxide as it is. Okay, and now what we're going to do is we are going to transfer a proton. We're going to transfer a proton from our acid to our base. Additionally, we are going to pair our cation and the anion present in solution. Yes, so we aren't dissociating ammonium further. So ammonium stays in as NH4 plus, but this entire salt is a soluble ionic compound. So ammonium ion is our weak acid, and we do not dissociate this weak acid further. We do dissociate this salt further. Does that make sense? We dissociate the salt because it's an ionic compound, but we stop at ammonium because it is a weak acid and doesn't dissociate further. Okay, so in terms of our predicted products now, after transfer of a proton, we get ammonia. Okay, we get water, silver plus, and chloride. Now, if we pair our silver plus and chloride, so crossing our charges, silver plus, Cl minus, that gives us silver chloride. And now my question to all of you is silver chloride soluble or insoluble? Do we put a solid, liquid, or gas symbol? Is silver chloride soluble or insoluble? Insoluble, exactly right. So now what we do, now that we have our equation products established after we've transferred our proton, we write out each of our reactants and products. And we just check that this equation is balanced. We just verify that this equation is balanced. Okay, so as we can see, the equation's balanced. It has the same number of atoms of each element on each side. And are there any spectator ions in this case? Are there any spectator ions in this case? any spectator ions whatsoever? Nope. So our net ionic equation looks exactly identical as our total ionic equation. So for our acid-base reaction, all you do is transfer protons from your acid to your base. So in this case, this is a combination of an acid-base reaction, a gas-forming reaction, and it's a precipitation reaction. So it's a 3-for-1 in terms of characteristics. Give me 1 second to reset OneNote. I'm just noticing a little bit of lag, and I don't want that to get too distracting for everyone. So we've seen one example. Let's do one more example of an acid-base reaction. So let's try to predict the products from the following reaction and draw a total ionic and net ionic equation for the following reaction. So we have a solution of sodium phosphate and sulfuric acid are mixed. Now, before I let everyone loose on this problem, let's get some formulas in place. Would someone like to propose a formula for sodium phosphate? Would someone like to propose a formula for sodium phosphate? Yep, so we have sodium plus, phosphate is PO4 3-. So that in turn gives us, after we cross the charges, we get Na3PO4. And we're mixing it with sulfuric acid, which is H2SO4. Now, in an acid-base reaction, you donate protons from your acid to your conjugate base anion. So I'd like you to take a moment and try to predict the products from this reaction after the acid-base reaction is complete. Once we have our products predicted, we'll balance the equation and then write a total and net ionic equation. So let's take about 4 minutes to work through this problem. Let's try to predict the products from this reaction. And don't be shy to message me with your proposed predictions for the products from this acid-base reactions, from this proton transfer reaction. Yep, I'm seeing some reasonable responses so far for our predicted products. So again, for our proton transfer, I like to think of acid bases as just fancy precipitation or exchange-like reactions. So what I'm going to do is I'm going to swap my cations. So, and then I'm going to write the formulas of my new compounds after swapping my cation. So I have sodium plus and sulfate, and I have H plus and phosphate. So I'm going to cross my charges, and that gives me H3PO4, phosphoric acid, and sodium sulfate, which is Na2SO4. Okay, so now that I have my products predicted, I am now ready to start balancing my chemical equation. So let's rewrite this chemical equation and let's focus on balancing the chemical equation. Notice I've left some of the state symbols blank because we're going to figure that out together. So it's intentional on my part. Okay, now looking at this equation, let's do a quick atom inventory. I have 3 sodiums, 1 phosphate ion. I have 2 hydrogens, 1 sulfate ion. I have 3 hydrogens and 1 phosphate ion. I have 2 sodiums and 1 sulfate ion. Okay, so is this equation balanced? Is this equation balanced as written? Is this equation balanced? No. Now, since we have the same ion on both sides of this chemical equation, I'm going to use the least common multiple method. So what's the least common multiple between 3 and 2? 6. So we're going to multiply our amount of sodiums, or sodium sulfates, by 3, and the amount of sodium phosphates by 2. So we have 6 sodiums and 2 phosphates. And now we have 6 sodiums and 3 sulfates. Let's do the same process for hydrogen. What's the least common multiple between 2 and 3? 6. So we're going to multiply our moles of sulfuric acid by 3. So we have 6 hydrogens and 3 sulfates. And we're going to multiply our phosphoric acids by 2, which gives us 6 hydrogens and 2 phosphates. Wonderful. So now that we have our balanced equation, let's just write our balanced equation. And while we're here, I'd just like everyone to think about for a moment, is our sodium phosphate soluble or insoluble? Is sodium phosphate soluble or insoluble? Soluble, yep, it's a sodium salt, so it gets the aqueous symbol. Perfect. Phosphoric acid. Acids are generally water soluble. Sodium sulfate. Is sodium sulfate soluble or insoluble? Is sodium sulfate soluble or insoluble? It's a sodium salt, once again, soluble, yep. Okay, so now we dissociate all of our soluble ionic compounds, strong acids, and strong bases. So I'm going to use a different color since we're dealing with our total ionic equation. We have 6 sodium plus, 2 times 3 is 6. We have 2 phosphates. And now my question to all of you, do we dissociate sulfuric acid? Do we dissociate sulfuric acid? Do we dissociate sulfuric acid? Yes, we do. And how many H pluses do I need to write? 6. 3 times 2 is 6. And we get 3 sulfates. Do we dissociate phosphoric acid? Is phosphoric acid on our table of strong acids? Remember when we discussed acid-base reactions, and in this chapter I gave you a table of strong acids. Is phosphoric acid on that table? Do we dissociate phosphoric acid? Yes or no? And at this time you should be flipping to the table in your notes, and let's take a moment to answer that. Do we dissociate phosphoric acid? No, we do not. It's not on our list of strong acids. Okay, do we dissociate sodium sulfate? Yes, we do. How many sodiums do I write for sodium sulfate? How many sodiums are generated in solution for sodium sulfate? How many sodiums do we generate? 6. Okay, perfect. And we also make 3 sulfate. Now let's cancel our spectators. And there are a lot of spectators in this case. So what are our spectator ions? What are our spectator ions in this case? Sodium, yep, exactly right. What else? What else? Sulfate, yep. Perfect. So for our net ionic equation, we have our phosphate reacting with 6H plus to yield 2 phosphoric acid. Now, can we simplify this equation? Can we simplify our coefficient? Is this the smallest possible set of coefficients? Yes. So then we can simplify this to phosphate plus 3H plus aqueous leads to phosphoric acid. And this is the typical ionic equation for a weak base plus a strong acid. So the reason why I teach you all of these reaction archetypes is because if you knew that this was a weak base and strong acid reaction, you could shortcut a large number of your steps to get to your net ionic equation. So the reason why this pattern recognition is valuable is because it can save some thinking time in terms of generating your reaction products and writing out your net ionic equation. Wonderful. Everyone's doing quite well at this so far. Let's look at one more reaction. This one's pretty interesting. So we have lead 2 carbonate added to a solution of sulfuric acid. Now, before I let everyone loose to work on this problem, let's first start by predicting the formula. Would someone like to tell me what is the formula for lead 2 carbonate? Yep, exactly right. PbCl3. Okay, sulfuric acid is our good old friend, H2SO4 aqueous. And now I'd like you to take about 3 to 4 minutes and try to predict the product from this reaction and try to write a net ionic equation for this reaction. Just remember, carbonate is a special ion when it participates in acid-base reactions. So remember what we discussed about carbonates. So we'll discuss this question in about 3 to 4 minutes. Mariana, your response is almost perfect. I would just double check the formula for lead sulfate. And we'll discuss this question in about two minutes. Yep, exactly right. And we'll discuss in about a minute and a half. Okay, so I see a lot of reasonable responses. So as always, I like to treat acid-base reactions as very fancy exchange reactions. So I'm going to swap my cationic species. Essentially what I'm doing in this case is I'm donating protons to my basic anion. So we have lead 2 plus. Just in terms of writing formulas, SO4 2 minus, we cross our charges and we predict to form lead sulfate. Now we're going to take H plus and cross it with CO3 2 minus, and that in turn gives us carbonic acid. What happens to carbonic acid immediately once it's generated? Is carbonic acid particularly stable? So when we observed in lab, when we treated carbonate salts with acid, we observed bubbles. And that's because carbonic acid decomposes to carbon dioxide gas and water. Okay, so now that we have our rough equation outline, let's write our rough equation outline and let's check to see if we need to balance this chemical equation. Let's check to see if we need to balance this chemical equation. Also, while we're here, we'll put some state symbols in because we need those. Okay. So, given the following equation, is this equation balanced? Is this equation balanced? Do we have the same number of atoms of each element on each side? Let's check. So I have 1 lead, 1 carbon, and 3 oxygen. I have 2 hydrogens, 1 sulfur, and 4 oxygen. I have 1 lead, 1 sulfur, and 4 oxygen. I have 1 carbon and 2 oxygen, and I have 2 hydrogens and 1 oxygen. So I'm just going to cross things out if they're identical on each side. So carbon crosses out, lead crosses out, hydrogen crosses out. 7 oxygens cross out, sulfur crosses out. So it looks balanced to me. Does everyone agree with that assessment? Is everyone comfortable with that idea? Okay, perfect. Now let's put some state symbols. Lead carbonate. Lead is a bit of a brick. Is lead carbonate going to be soluble or insoluble? So if we think about carbonates, they're not very soluble for the most part. Lead carbonate is insoluble. What about lead sulfate? Sulfates. Well, thinking about our exceptions, is lead sulfate soluble or insoluble? Does it get a solid or an aqueous symbol? And don't be shy to refer to your table, though the further we get into this chapter, the less and less I want you to be referring to that table and the more I want you to be recalling from memory. You want to develop your skills to the point where you can recall these solubility rules on an exam from memory. So is lead sulfate soluble or insoluble? And I'd like to see a response in chat just to make sure that everyone's looking at the table and everyone's comfortable with assigning solubility. Insoluble, exactly right. Thank you. Perfect. Oh, whoops. Insoluble, so it should get a solid symbol. Getting ahead of myself here with this next portion. Okay, now that we have a balanced equation, we're going to dissociate all of our soluble species. So we're going to dissociate all of our soluble species. I don't know why I kept putting aqueous when they should get a solid. So both lead carbonate and lead sulfate are insoluble. So then, looking at lead carbonate, do we dissociate lead carbonate? Do we dissociate lead carbonate? No, we keep it together because it's an insoluble species. Do we dissociate sulfuric acid? Is sulfuric acid a strong acid? Yes, so we dissociate to 2H plus aqueous and sulfate, SO4 2 minus aqueous. Lead sulfate we keep together because it's insoluble. Carbon dioxide and water we keep together. Now, are there any spectator ions in this equation? Are there any spectator ions in this equation? Are there any spectators, or is this equation perfectly fine? Are there any spectators, or is this equation perfectly fine? There are no spectators, so then our net and total ionic equation are identical. Perfect. Wonderful. Any questions on this example before we move on? Okay, let's keep going then. So we've reached a good stopping point for today because redox reactions are going to take us the entirety of next class session. So we've reached the desired stopping point for today. So I'd like you to just do a little bit of pre-reading on redox reactions and review writing oxidation numbers. I would especially look at the bleach lab pre-lab lecture. We're going to be dealing with redox reactions the entirety of our next class session. But here's a good stopping point for this